Well, it's always a pleasure to visit the Astronomical Society of Victoria, so thank you to everyone for coming out tonight. Tonight I'll be talking about astronomy with an E. What does that all mean? Well, I wanted to just first of all test your knowledge. It's important to understand what you know before I go too far into any topic. So here's some quick questions for you. What's this? Fantastic. Anglo-Australian, I keep calling it Anglo-Australian, I have to call it the Australian Astronomical Observatory. Old habits die hard. Any ideas? MWA, the Murchison Wide Field Array. These three facilities all have something in common. Does anyone know what that is? They're all in Australia, fantastic. They produce a lot of data. They're also three of our national facilities. And we actually have one more national astronomical facility, and it's this one here. Does anyone know what this one is? It's the supercomputer at Swinburne. It has a name, it's called gSTAR. One of these many tortured acronyms, the GPU Supercomputer for Theoretical Astrophysics Research, or as I like to think of, Australia's first fully indoor national astronomical facility. So I'm going to try and talk to you tonight about this facility and why places like this are changing the way that we think about the universe, and actually also changing the way we think and do science. So let's go backwards in time just a little bit. There's sort of a haze going over us. We're going back 6,000 or 7,000 years to the birth of astronomy. Now, I can't call it a science at this point because it didn't have many of the characteristics that we require of science, but it did involve observation. In certain cultures it involved recording, even occasionally predicting, but it was about monitoring what was going on in the sky, recognising that there were patterns, regular motion, and that these were repeating each year in some kind of fashion. So out of that, over time, people began to try and explain what was going on. And so in cultures like ancient Egypt and early civilizations, it was really about supernatural explanations for things. It was the gods were controlling the motion of the objects in the sky. And it was only around 500 or 600 BC that the natural philosophers began to say, no, it's not the gods doing things. There are other reasons why the sun moves, the moon moves, the planets moves, the stars move. And so we started to see the birth of more scientific thinking, but still quite different to science as we understand it now. It was very much about, I think this is how it works, and I'll give you a complete picture of it, but some of the other things we would ask of a science weren't there. At some point, the first, what you could think of as experiments began, and experimentation is a really important part of science. And Eratosthenes, who famously measured the circumference of the Earth by noting that in one location during the solstice that a stick would cast a shadow, whereas elsewhere there was a well, and at the solstice the sun shone straight down the well. And if you believe all of the elements of the story, which involve carefully pacing out an enormous distance in the ancient world, he was actually relatively accurate. He got the technique exactly right, and some of the details not quite. But he was very close to our modern circumference of the Earth. So we start to see these testing ideas begin. But the experimental method, as it might be more recognisable to a modern scientist, didn't really get established until about the 11th century. And Ibn al-Haytham, an Islamic Arabic world astronomer, more generally, I guess you could call him also proto-physicist, wrote a book of optics which is the first recorded example of something closer to an experimental technique. Roger Bacon, a 13th century monk, was then the first who sort of said that, well, science is about a process of observing, hypothesizing, experimenting, and then verifying, and then going back through the process again. So this is really where science as we know it. So within astronomy, though, as we all know, experimentation is a little bit difficult. And instead of the controlled direct experiments that happen in other fields, much of astronomy is about observation and recording. So over the last 400 or so years, we've had increasingly powerful telescopes providing greater and greater observations, a variety of new types of instruments to collect the data that also needed a theoretical explanation. And really, the first time that a consistent, complete and coherent explanation of how it all worked came with Isaac Newton's Principia in 1687. So at last we had most of the elements now of science. We have experimentation, we have increasingly powerful methods of observation, we've got a theoretical basis with which to compare things, and things are looking good. And this worked incredibly well for 300 or 400 years until a disruptive technology came along. And really what you see a lot of the time in any science is the big changes happen when a new unexpected technology comes in and gives you a capability that you didn't have before. And in the 1940s, that disruptive technology was the computer. The first computers filled rooms, didn't have a great deal of processing capability. All of our mobile phones have very much more processing power than some of these early computers. And if you think about the time, the late 1940s, a lot of the interest in using these facilities was to study uncontrolled nuclear reactions. Most of the effort was looking at nuclear weaponry, but there were some astronomers who got interested because the same types of equations were explaining what was happening inside the sun and other stars. By about the 1990s, nearly 10% of astronomers were involved in computational astronomy of some sort, and I would guess that it's getting up towards closer to 20 to 30% of modern astronomers would consider themselves computational astronomers. So we have here three, what we can think of as research paradigms or ways of thinking or doing science. We have an experimental paradigm where you test an idea by performing, hopefully, a controlled experiment, seeing what happens, modify your experiment, do it again. We have a theoretical approach to science where you start with, less so these days, a pen and paper. You're more likely to use a computer these days to do most of your theoretical work, but it's more about trying to find equations that mathematics that explain physical processes. And then you have the computational side, which is using these advanced computing techniques to do the theoretical computations that are not feasible to do by hand. Well, we now actually have a fourth paradigm that's growing, and we're beginning to understand what it means, but we're very aware that it's going to have an enormous impact on it. And it's called, perhaps less interestingly at this point, massive data exploration. You might sometimes hear it referred to as e-research or e-science. And I'm not sure any of us really know what the E stands for, to be honest. We all have an email account, and we probably think we know what that means. But really we're talking about discovering knowledge, just doing your science purely on the basis of a massive amount of data that you've collected somewhere. One of the pioneers of this was former computer scientist Jim Gray. I have a somewhat strange date of death for Jim. Jim went missing while sailing his yacht in San Francisco Bay in 2007. And although there was a very large search for him, the yacht was never found. and he was officially declared deceased in absentia in 2012. But he was really one of the pioneers. He won the Turing Prize, which is the equivalent of the Nobel Prize for computer science for some of his work in databases. And in the early 2000s, he really established this field of e-science and e-research, particularly within astronomy, working with Alexander Saleh from Johns Hopkins. And he said here in a Microsoft research white paper that all astronomy data and literature will soon be online and accessible via the internet. So the internet was the other disruptive technology that had to come around here. And for the last 10 or 15 years, there's been a lot of interest in what we call virtual observatories, moving away from actually going to a physical observatory to take data, but instead looking at the data that's being collected at a telescope somewhere else in the world. So I need to just talk a little bit about computer storage, just to make sure that we've all got a common understanding of what the problem is and what we mean by massive data exploration. So many of you, if not all of you, are familiar with the concept that any hard drive or any other storage mechanism we have for computer data ultimately breaks things down into what we call bits. Everything is either a 1 or a 0. And we start to combine these bits together, binary numbers, into a particular notation. We talk about a byte being 8 bits, and you can start to learn to count quite effectively. So here we have the numbers 1 to 10 written in binary. A great party trick is if anyone ever asks you what's the biggest number that you can count to on your fingers, the answer is 1023. And the way that you do it is that each of your fingers now becomes either a binary digit that's up or down. So they're all down, it's 0, they're all up, it's 1023, and some combination in between, some of which are incredibly rude to make, and some are just quite challenging. Your fingers don't want to bend that way, but in principle you can count to 1023 on your fingers. So on a computer though, we have to make a decision about exactly how we wish to store our data, and we start to have these very exciting conversations about 8-bit integers versus 32-bit floating point numbers. And I've just shown here a very important number, 42, expressed as an 8-bit integer, and then the same as a floating point number. And the important message here is that computers aren't perfect. We actually can't store a number with infinite precision. So anytime something gets written to a disk, if it's a number with a great number of decimal locations in it, we can't always store it very accurately. There's clever techniques to help you, but often it's an imperfect record of what the original data was. So a byte is not a terribly useful measurement on its own, only 8 bits. We start to look at sizes, and you can all think back on your first computers or some other storage device that you had. My first computer back in the 1980s had 16 kilobytes of memory, and we thought that was fantastic. My dad did such a wonderful job buying us 4 times what had been recommended, and was assured we'd never have a program that would need more than 16 kilobytes of RAM in it. But we go up in essentially factors of 1,000 here, from kilobytes to megabytes to gigabytes. The present, we're starting to buy terabyte disks at home. I think I always judge how storage is going by how much Dick Smith or Officeworks will sell you a disk for. And I remember at the start of my PhD studies that thinking about buying a terabyte was tens or hundreds of thousands of dollars. Now it's about $100 for a terabyte of data storage. So many of you at home will have maybe a few terabytes, and so a petabyte now, 1,000 terabytes, is sort of the current boundary of where you go from a home user onto a more sophisticated data storage solution. And we can continue this as often as we like in factors of thousands, exabytes, zettabytes, yottabytes. And eventually we'll need to keep producing more names for these. To put that in context, how we've looked at our own supercomputer storage at Swinburne University over our two most recent facilities. The Green Machine on the left, which commenced operation in 2007. We thought we were doing a fantastic job because we had 100 terabytes of disk storage available. The Green 2 facility, which is gSTAR, this national supercomputing facility, and a complementary machine called SwinStar has 1.7 petabytes, and we're looking at expanding that again fairly soon. So it's only really a factor of 10 in disk storage in the last 5 years. And this is one of the challenges for massive data exploration, is that computer processing power is growing significantly faster than disk storage capacity and also disk access. It takes a very long time in many cases if you need to read a few hundred terabytes of data from one location to another. So in the last decade, astronomers like to introduce words, phrases that give us a sense of what's happening. Data avalanche, data deluge, data tsunami. We're all going to be overwhelmed by the quantity of the data that's coming in because we're not actually completely equipped to deal with it. The data fire hose, sort of telescopes just producing so much data, it's spraying out everywhere, and we have no easy way of capturing it and interrogating it. One of my colleagues, I have to give him credit, David Barnes, for the data cliff, in analogy with the fiscal cliff from a few years ago, that we're again, a sort of catastrophic situation if we don't do something radical. So just how big do I mean by big data? Well, this is one of the projects that really changed the way that astronomers thought about large data, and it was one that Jim Gray was involved in the planning of the data infrastructure for. This is the Sloan Survey Telescope at Apache Point, and I hope that you've all heard of the Sloan Digital Sky Survey or seen some of the results from it. It's quite a small telescope as far as professional instruments go. It's only a 2.5 metre primary, but it has a very large secondary, and that gives it quite a large field of view. And the goal with the Sloan was it's not a telescope that you apply for time on or look at particular objects of interest. It just maps the whole sky, and it does it quite continuously with a very large 120 megapixel camera. There have been 3 phases of the survey. The initial survey was a 3 or 4 year project just to see how it went, and it was so successful that a second phase was then approved, and a third phase which is now nearing its end. And there's something, depending on which website you go to, there's somewhere between 60 to 150 terabytes of data. That includes the raw images coming off the telescope, but also the processed data, the catalogues and everything else that comes with it. There have been 10 individual data releases, and there's an 11th that's due next year. And so far they've mapped very accurately not only imaging, but taking spectra to get positions, 930,000 galaxies, 120,000 quasars, and many millions of stars have now been imaged. So some of the lovely results that you can get, this example here, it's called the field of streams, and what we're looking at is a patch of the Milky Way where the colour is telling you how far away each star is. So each dot in this image is a star. The things with circles around them are companion objects to the Milky Way, some new globular clusters and some new dwarf galaxies. And the density of the points is telling you, the intensity is telling you something about the density of stars in that particular region. And so you see these very large coherent connected structures or streams, and these are showing you the evolution of the Milky Way. We believe that our Milky Way as a spiral galaxy was built up through a series of minor merger events where small proto-galaxies got gravitationally attracted to a slightly larger object and got completely disrupted, and their stars all then formed into the Milky Way. And this process went on over quite an extended period. And so each of these large features in here is essentially the leftover of one particular merger event that had happened in the past. So we have this new field, it's called galactic archaeology, or in this case stellar archaeology, unwinding the history of how a Milky Way was built up by looking at features like this. Another interesting thing you can do is look at all of the quasars, and here we now are looking at the what's called the spectrum of the quasar, the breaking up its light into its components. And along the bottom we have wavelength from blue on the left to red on the right, and then quasars at different redshifts, which is essentially just saying at different distances from us. And we see particular features in the spectrum, Lyman alpha from hydrogen, some carbon lines, iron, magnesium, oxygen, and you see that they're all continuous through this redshift space. And this is allowing the particular project involved looking at this to do things like measuring the expansion history of the universe, just from these incredibly detailed amounts of data that they have. So somewhere between 60 and 150 terabytes is quite big data. I can't put it on my home PC. I have to look to quite a large data center to store that. I have to think very carefully about how I access it. Anytime I want to move the data to another location, it's not trivial. I can't just download it all over the internet. It would take far too long. But that's just the tip of the iceberg, because this is a facility that's currently in the planning stage. This is considered the most important future goal, particularly in the United States, in their recent decadal plan, the Large Synoptic Survey Telescope. It's now an 8.4 metre diameter primary mirror, just over 3,000 megapixel camera. And when it's in operation, probably still 10 years away, subject to funding, every night it will generate something like 20 to 30 terabytes. So within 4 or 5 nights, it's produced what the Sloan survey took about 8 years to do. So over the 10-year lifetime, we're now talking about 60 petabytes just of raw data, and that's not assuming that they're not going to upgrade their capabilities before then. So this is serious big data. This is about almost as big as it gets in the near term in astronomy. So we have a change now in the way that astronomers need to work, and unfortunately they haven't all realised it just yet. Most astronomers are still working in a mode where they record their data at a telescope, put it onto their desktop computer and analyse it. We can think of that as taking the data to your computer to do the computation. And at the moment that works incredibly well if you're talking tens or hundreds of gigabytes of data. Once you start to talk about terabytes of data, that exceeds what our desktops can do as far as the memory. You can get it on disk, that's okay, but it's very slow to access. You can be sitting there for hours waiting for your data to load and be processed. And that's not always the most practical. If you're trying to really understand your data, quite often you want an instantaneous response. You don't want to ask a question of your data and then wait 4 or 5 hours for the answer, because you've forgotten what question you asked and why you're asking that. And on the petascale, there's no way you can do that on your desktop. You need to move into a new mode of thinking, which is taking your computation to the data using what we call a remote service. And that's how myself and some of my PhD students have been thinking about gSTAR as a facility. It is mostly designed to do these sorts of large-scale computational problems, simulating the structure of the universe over billions of years and these kind of massive scale simulations. But I like to think of it in a quite different way, as a simple way of producing lots of data but also as a way of combining together an enormous processing capability in one go to do real-time analysis of very large data sets. So I'd like to now talk then about two particular projects that my PhD students have been working on in recent years. The first one I'm only going to cover in the very briefest of detail. I could have talked the entire night just about this. This is Yorgos. He's now nearing the final 12 months of his PhD, and he's working on a project that I take full responsibility for the title GALUMPH. It's the GPU-enabled cosmological... I'm even going to get it wrong tonight, aren't I? The GPU-enabled high-resolution cosmological microlensing parameter survey. So what on earth does that all mean? So here's quasar microlensing in a nutshell. One of the predictions of Einstein's general theory of relativity was that if you have a massive object somewhere in the universe and it's on the line of sight to a more distant object, that you'll get multiple images of that background object. And you can see the classic example in the top middle there, quasar 2237 plus 0305. It's a 4-image gravitationally lensed system. Each one of those 4 images is a multiple lensed image of a single background object called a quasar. And if you monitor this over time, what you'll see, let me bring up, see if I can get a cursor going. Here we go. Along the bottom, we're looking at measuring the brightness over a series of days. So this is over a couple of years of data, and forgetting the exact magnitudes, I can actually say magnitudes in front of this audience rather than those crazy astronomical units for measuring brightness. But if you look at our reference star down the bottom, it doesn't change in brightness at all over time. There's maybe a tiny bit of variation, which is probably more an instrumental thing than a true variation in the star. But all sorts of crazy things are going on in my 4 images. Initially, A, B, C, D was ordered in terms of brightness. So A was my brightest down to D my faintest. But then at some point, C suddenly got a whole lot brighter than B, and then it got even brighter, and then A went up even further, and D came down. And these individual variations are very important because we can actually probe the properties around the central supermassive black hole in a quasar at enormous distances from us. So I don't want to go into all of the technical detail of how that works, beyond saying that at the moment we only know of about 100 of these systems, and so it's been reasonably easy to keep track of them. But when the Large Synoptic Survey Telescope comes online, we will suddenly find thousands of these. And so what Yorgos has been doing is some of the original preparation for those new discoveries. And he's doing a lot of computation. There's the equation that he has to solve, and the outcome is we get these things called magnification maps, caustics, that tell us how often we expect particular changes in brightness to occur. So why is this a big data problem? Well, I asked Yorgos, could he just put all this data online? Because we thought we would ask the rest of the astronomy community to make use of it. So here's a web page that you can actually all now go and investigate if you really want to. It's not officially released, so buyer beware. But you can do your own astronomy research before we've even looked at most of the data. If we zoom in on the bottom, so far Yorgos has created 46,000 of these magnification maps, 17.4 terabytes, and the equivalent of 17,000 computing days on gSTAR. We've been very lucky to be some of the first users, and so we have shamelessly monopolized it while we could. So 17 terabytes now becomes quite a large resource for people to access. But one of the aspects of this new massive data exploration and using the internet to support it is to provide tools that you can use that are taking computation to the data, and so providing what we're calling e-tools in a web browser that allow you to request any one of the 45,000 maps, and this is just showing you the particular parameters that came with this map. Yellow here, the numbers aren't as important to discuss, but what's more important is that we have nearly 50,000 of these maps that can be queried.
There's a laser.
There is? Excellent. So these three numbers here, these three numbers are just telling you something about the properties of that map, and then we can do all sorts of analysis on it. We can start to build these fun tools that you can play with where you can colour these maps in order to help understand and all sorts of analysis. So all of this is now available to astronomers to use as an e-research tool. But what I do want to talk in a little bit more detail, though, as my final topic, is the work that Dr. Hassan, who completed his PhD last year, terascale visualization and data analysis. So, as you're also hopefully very aware, the Australian Square Kilometre Array Pathfinder, or ASCAP, is now well and truly under construction and heading towards first science. It's a radio telescope that will ultimately comprise 36 antennas linked up together. It's using a new technology called a phased array feed that allows you to image a number of different directions on the sky at the same time. It's a telescope with a very wide field of view, so it's designed to do surveys of the entire sky on short time periods and quite a broad range of observing frequencies. It generates data, 9 terabytes of raw data every second. So we've gone from the LSST producing something like 20 to 30 terabytes a night to 9 terabytes every second. 120 million Blu-rays being reliably informed every day. But we don't actually have the capacity to store this data. So once we record it and do some manipulation, some calibration, and turn it into a final data product, we throw the original data away. So we start to talk about this concept of not having a computer archive, but the sky is the archive. It's more easy to go back and observe again than it is to store the data. And that's quite a fundamental change. So we were particularly interested in one project called Wallaby. It's a search for hydrogen gas in nearby galaxies. It's one of the largest data generating projects planned for the Australian SKA Pathfinder. It's hoping to cover something like 75% of the sky and detect 500,000 new galaxies just from the neutral hydrogen, looking back something like 3 billion years. So in some sense, still quite a relatively nearby search. And the main product that comes out of these things called spectral data cubes, which have 2 sky axes, so right ascension and declination, but also a frequency channel which is related to the velocity along the line of sight to us. And using an equation that just tells us the observed frequency where we observe in this channel, this axis here, is related to the velocity at which that material is either moving towards or away from us. And so when you look at the Milky Way, and nearby, very nearby, it looks something like this. This is the Large Magellanic Cloud. This is the plane of the Milky Way galaxy through here, and these little tiny blobs in here are other galaxies. This is the entire, what's called the High Pass survey that was conducted with the Parkes telescope. It took something like 7 or 8 years to look at 387 different patches of the sky, and this is bringing them all together in one place. It's 12 gigabytes of data. So I could practically put this on a USB stick today, whereas at the time, this was big data. So the likely data product for Wallaby goes from high pass being 17,000 by 17,000 up to 4,000 by 4,000 sky pixels, 1,000 frequency channels going up to 16,000, or something like 1 terabyte per cube, and nearly 1,200 of these cubes across the entire survey. And a question that we asked just over 3 years ago was, can we support real-time interactive visualization and data analysis? And I like to just cut to the chase, and the answer was yes, we can. And this is, in a few seconds, 3 years of incredibly hard work from Hassan. This is the entire high pass replicated 48 times, so it's half a terabyte of data, and he was actually able to visualize this on gSTAR, using most of gSTAR, at 7 frames per second, which is just amazing. There's nothing else we've seen in the world that can do this level of data visualization. If you're interested in how it works, this is the general idea. Our astronomer sits on this side using whatever type of display they want to use, and they connect via the internet, and they send a signal saying, I want to turn the data around and look at it from a different angle. It goes to a server that then splits that up across each of the GPUs, graphics processing units on gSTAR. A GPU is essentially a games card that we can now utilize to do science processing. And then each GPU creates its piece of the picture, sends it back, and that goes back to the astronomer at the other end. So again, it's moving the computation to where the data is sitting. It's quite easy to transfer a small image back and do all of the work behind the scenes. And this is now essentially, as far as we're concerned, solved all of the visualization challenges of Wallaby project. In fact, most of ASCAP's big visualization challenges a few years in advance of it being needed. So here is the actual extra numbers in here. The real size, 540 gigabytes, about half a terabyte. We use 96 GPUs. But not only can we look at pictures, that's interesting, but also doing analysis, actually getting a statistical quantity out on data sets this large is incredibly difficult. And ARM's solution can get the standard statistics in a few seconds, up to about a minute, which is amazing. So we think we've got this under control, as long as graphics processing units keep getting faster and cheaper as they have in recent years, that we can not be quite so frightened by what's coming over the horizon, which is the square kilometre array itself, where now we're going to generate 1 exabyte per day, 1,000 petabytes every day. In the first few seconds, that's more data than the entire history of astronomy. In the first few days, that's more data than the history of just about everything that's ever been recorded. Twice the global internet traffic that currently exists is required to do the processing, and the combined top 250 supercomputers in the world extrapolated forwards by 10 years in order to make this thing run. So it's quite an amazing project. And you do have to ask, if we're not preparing now, what on earth will we do with this data when it comes? So to me, astronomy with an E, it's the exascale. It's looking over the horizon. It's thinking about the ways that astronomy research is changing. We need both evolutionary and revolutionary changes in the way that we do science. This exploration in massive data sets is really what astronomers of the future will do. We won't have observers as we think of anymore. We may not even be able to employ theoreticians or computational astronomers, because we'll have so much data that the only way we can make any progress is if everyone is working with this massive data exploration. It's introducing new words that I'm not even sure that I know what they mean. Astroinformatics. It's kind of like bioinformatics, only it's with astronomy data. Knowledge discovery in databases. Data mining, searching for new knowledge, or as Kirkborn said, we're already doing data mining. The data are mine and you can't have them. But this is really about sharing data. Everyone will have data almost instantaneously. We won't have this mode. ASCAP is quite revolutionary in that the science teams working on planning don't get proprietary access to the data. as soon as the quality control phase is done, it goes live. And anyone, anywhere in the world can start doing science with it. That's quite amazing. But finally, you can tell when a discipline or a subfield truly has become important because they produce a journal. And it's only been in the last 12 months that it's been recognised that there is a great deal of work that's important that's going on the boundary between astronomy and computing. We're too, I've found as someone who's published in this field for a decade now, I'm too computational for the astronomers and I'm too applied for the computer scientists. So it was a huge privilege for me when I was asked to be one of the founding editors for this new journal. And we've had our first issue coming out and we're very close to having our second issue. So it's great to be at the forefront of this brand new, very exciting discipline. And I hope that in the era of massive data exploration, we'll finally get to see what the big picture truly is. Thank you.